Okay, so let's study about von Mises strength criteria. Von So, the loading function von Mises strength criteria is F. This is a square root J2 minus K. K is a material constant. So, stress state should be satisfy this condition. If this condition becomes zero, it means the material failure happened, right? J2 is the second invariant of deviatory stress, right? So today the first topic I like to teach is a concept of von Mises strength criteria. Let's plot principal stress space defined by three principal stress direction N1, N2, N3. This is a principal stress space. Okay. So here we have origin. So in principal stress space, all the stress state can be given by three number, right? Sigma 1, 2, 3. These are the principal stress, right? And if three principal stress has the same value, we are saying this is hydrostatic pressure, right? So when three principal stress is same, all the stress state can be in this line. Let's say this is a principal stress axis, hydrostatic axis. Hydrostatic axis. And 1 over square root 3 and 1, 1, 1. And let's consider some arbitrary stress state given at point P. Here, stress 1, stress 2, stress 3. I like this point. This can be given by this point can be given by some vector. Okay, this is vector OP, right? And I like to project this on the line N. Then we can decompose this OP vector in two parts, ON and NP. So vector OP equal ON plus OP. Right? This is point N here. So let's calculate the magnitude of ON. How can I calculate that magnitude of ON? From here to here. If you take the dot product, this OP vector and hydrostatic axis, we can find, right? This is dot product. So this means projection OP into N. So calculation is simple. Sigma 1, sigma 2, sigma 3, and here this is dot product, right? Then 2, 3. This is magnitude of the vector ON, and this is become root square 3 sigma m. Sigma m equal 1 over 3 sigma ii, right? So ON mean so hydrostatic part, okay? And vector ON. So since we know the magnitude and direction of vector ON, we can find ON equal root square 3 sigma m and 1, 1, 1, right? So this become sigma m, sigma m, sigma m, right? So position over here is a sigma m, sigma m, sigma m, right? Mean stress. Sigma m is a mean stress. And then now we can find the distance between two. Magnitude, bit O, NP. How can I calculate the NP? This is just distance, right? Very simple. That NP will be from the Pythagoras theorem, sigma 1 minus sigma m square plus sigma 2 minus sigma m square plus 3 minus sigma m square, right? This means S1 square plus S2 square plus S3 square. Right? And this is the same to 2J2. So here we now know the very important concept J2. This is J2. square root 2j2. Square root 2j2 physically mean the distance from the hydrostatic axis, right? So, in bone Mises strength criteria, okay, distance from the hydrostatic axis govern material failure, right? If the distance from the hydro axis is bigger than something, okay, material fail, or bigger than something, smaller than something, material doesn't fail. Understand? So when material fail, so J2, when J2 equal K, material fail, right? So J2 equal and 2J2 equal root 2K, right? When the distance from the hydro axis is bigger than root 2K, the material fail. So based on this concept, we can plot. This is a hydrostatic axis and some cylinder like this. Okay, this is cylinder. And it has a R equal root 2K, A2. This is cylinder, right? And 1, and 2, and 3, right? This is cylinder. You can imagine. So, material stress state is within this cylinder, inside of this cylinder. Okay, material doesn't fail, and that stress state is admissible. Admissible means that's the possible stress state. But stress state is meet the surface of a cylinder, material start to fail. And stress state cannot be outside of the cylinder, right? Understand? And von Mises criteria physically mean for hydrostatic stress state, material never fail, right? Right? For hydrostatic stress state, stress will be always on the hydro axis. So line, this N line here, right? Never fail. So this is a cylinder here. So long times ago, von Mises did a lot of experiment by giving the three-dimensional stress 1, 2, and here stress 3. And he changed the ratio between stress 1, 2, 3, and then try to find the when material fail. And then he can put the many experimental results on this the principal space plane space, and then finally he found this kind of envelope. And also This is 3D, right? How about in 2D, N1 and N2 plane? Let's say this is N1 and N2 plane, right? In N1 and N2 plane, okay, what going to be shape of this cylinder? You cut this cylinder with the N1 and N2 plane. Huh? How? You will have some ellipse, right? So in N1 and N2 plane, so let's say N1 and 2 plane, you will have this shape. This is the envelope of von Mises criteria. And you know Tresca. Tresca have an envelope like this. Okay, so something like this, hexagon type. This is a Tresca and bone. So Tresca criterion have a hexagon type here, embedded in here. So in 3D, Tresca strength criteria have a hexagon cylinder, right? So now I'll give you an example. So let's say we have a bar here. This is a steel bar. Let's say steel bar here. Okay, and I like to give some tensioning force P, and which has the area A, and P here. So tensioning force P will be applied. P. This example. O bar. And this is steel bar, and I like to find the P, when the maximum P, okay, which can be applied. So I wanted to calculate the P critical. So critical load. We are saying this is critical load. When the externally applied the actual force P become critical load, P critical, this bar fail, start yielding. Okay? So I like to find that critical load. And I like to use von Mises. Von Mises value criteria, strength criteria. Okay. So material constant is K. K is given, right? So how can I calculate the critical force P? First of all, we need to think about the stress. So in this bar, okay, so let's consider the stress state. So here, this is a one-dimensional stress state it has. So here sigma 1, sigma 1. And sigma 1 equal P over A, right? And sigma 2 and sigma 3 is 0. So sigma 1 is a stress in x direction, 2 is stress in y, 3 is stress in g direction. So this is just a simple direct extension test, right? So stress state will be given by sigma 1 and 0, 0, right? And when material pair, so square root J2 equal K, then material pair. So what we need to do is to calculate J2. So let's calculate J2. So then we need to separate the stress field in two parts, deviator part and volumetric part. So sigma m will be 1 over 3 sigma 1, right? Because sigma stress 2 and 3 are 0. So stress deviator will be sigma 1 minus 1 over 3, sigma 1 minus 1 over 3, sigma 1 minus 1 over 3, sigma 1. This will be a stress deviator. Because the equal minus sigma mi, right? Let me check it. Right? Right? Then this is 3 to sigma 1. What's the J2? J2 will be a scalar 3 to sigma 1에 1 scalar and minus square plus square, right? Then it becomes two, 4, 1, 1. Okay, so square root 3 to sigma 1 square. Is that true? Is that right? Okay. So square root j2 equal k mean square root 2 over 3 sigma 1 square equal k. Right? This is a failure condition. So let's say this sigma k is sigma 1 is a critical. So sigma 1 critical will be k square and 3 over 2. Right? This is a critical load. Then how about the P critical? Critical multiply area equal k square A. This will be a critical load. Okay, understand? Any question? So this bar have a material which fail based on von Mises strength criteria have a critical load P critical. So that bar fail when critical load, this amount of critical load is applied. Okay? So this will be a maximum load possible. Okay, any question? Yeah, sorry. Right? This is right. Okay? Yeah, sorry. Sorry. So we need to have a square root.
j2가 루트 3분의 2 시그마 1 스퀘어. 두 번째 줄로 갈 때 k가 스퀘어.
Here?
첫 번째에서 두 번째로 넘어가는 j2가 루트 3분의 2.
J2. 오케이.
루트 j2가 되고.
Sorry. This should be root. J2. J2 should be like this, right? Okay, right. That's my mistake. So, also, based on that equation, we can calculate the K, right? So, for example, let's say we are doing some experiment, bar experiment, right? There is some machine which can pull the bar, and then we can find the critical load. So we can find this load from the experiment. So because we know the area, we can calculate K. So once we calculate K, we can use von Mises material strength criteria for that structure with that material, right? Okay. So von Mises strength criteria need just one experimental test. Okay, because it has only one strength parameter. Tresca have a 1, 2, right? Tension cord also 1, but Moore Coulomb has a 2 material parameter. So in Moore Coulomb case, we need to do 2 experiments. In finite element analysis, the software give effective stress, right? That effective stress means this J2. Okay, so if you compare that effective stress with the strength, here the K, we can find material failure happen or not, right? So you should know that the fact that effective stress is J2. Okay, so let me finish all the discussion on the strength. And so let's recall what we did before. First, we study on deformation, then strain, then momentum balance, and stress, and then strength, right? And what's next? Okay, so next is elasticity. And material law. This is a topic we have today. Let's say we have a body, okay? Here, in this body, let's say this body is V0. We used the omega 0 before, so omega 0. Usually, in structural mechanics, this body is properly fixed. Okay, this body is properly mean we can rid of a rigid body motion. So this body is fixed. It means there are some displacement boundary condition. So displacement is 0. And after applying some force, two kinds of force is possible: body force and surface force. This body will deform. So this is a deformed body. So omega t. And this is just external force. Let's say T, D. In this deformed situation, equilibrium should be satisfied, right? On the surface and in the body, and displacement boundary condition should be satisfied too, right? You already know about that. The very important thing is that all the equations should be satisfied on this deformed configuration, not the initial configuration, right? Okay, that's very important concept. And from that, because of that external force, body is deformed and there will be a displacement U, right? The difference between the initial position and deformed position give us displacement. And inside the body, we will have some strain. So strain Ij. Also, to satisfy the momentum balance, I mean, to satisfy all the equilibrium, we need to have stress inside of the body, right? So, in the analysis of solid and structure, what we wanted to find is that first, stress and strain and displacement at all the point of body, right? All the point of body, we need to find stress, strain, displacement. These are unknown, and these are unknown. These are all the things we should find and we need to find. And these will be used for the design of structure, right? So once we know stress, we can check whether this structure fail or not. So I mean the material failure. If we know the displacement, we can check the design condition on the deformation. So because there are also design conditions for deformation. If the deformation is too big, that's not good for, for example, so here we have, you are living in some tall building. So one of you are living here. So due to the wind, they're going to deformation 10 meter. You will feel very bad, right? So this will be a design condition for displacement. And actually, this will vibrate. Even this tall building doesn't fail. People don't like this kind of large deformation, right? So anyway, to design some engineering structure, we need to see all the facts, okay? We need to find this. So how many unknown we need to have? So we have at all the material point, we need to find stress. How many stress? Independent stress we have. 6. Because of stress is symmetric, 6. Over strain. Strain is symmetric, 2. So we have a 6 unknown. Displacement. X, Y, G, 3. Right? So total 15 unknown. That's so at each material point we have a 15 unknown. So and equation we know. Equation. Which equation you know? First, local equilibrium equation. Plus rho F minus rho gamma equals 0. And strain. U. So I think these two are all the equation you know. How about first equilibrium equation? How many equations we have for local equilibrium equation? This is 3 equation, right? In x direction, y direction, z direction. So 6. This from the linear momentum balance. How about angular momentum balance equation? There are equations for angular momentum balance. That also included because here we used stress is symmetric. So we have a 3 angular momentum balance equation, right? So if I wanted to put that equation here, I need to increase this to 6 to 9. Okay? Okay? If I don't consider, if I just consider 6, then we cannot include that angular momentum balance. So same thing actually. How about the stress displacement relation? This is equation. You know the stress displacement equation. Strain calculate from stress. In small displaced case, this was a 1 over 2 x uij okay, so uij plus uj xi and ei ej. This was a small strain, right? So how many equations here? Strain has a 6 independent. So for each strain we have an equation. So this means 6 equations. Sorry, this is 3 equations. So how many equations we know right now? Okay, 9 equations. 9 equations. So we have 6 equations, but we have 15 unknown. Right? This is a situation at this time. So how many equations are missing? 6. So 15 minus 9 equals 6. Equations are missing. So we need to find that missing equation from the elasticity and material law. So actually that 6 equation will come from the relation between stress and strain. Okay, strain have a 6 component. Stress have a 6 component. So if we have a relation between both, it will be a 6 equation. Then we can find the final 6 missing equation. Then our governing equation is complete. So we can find solution somehow. Understand? elasticity. What's the elasticity? You know elasticity. What's the elasticity? 정호, can you explain elasticity?
Material property of to when the material get force outside and then it is deformation, but when force is erased it is back.
Back to original position? Yeah, that's right. So elasticity is a reversible process. Of material or structure. So elasticity can be explained by simple spring model, right? Let's say we have a spring here. So I'm going to pull this spring with some force P. Okay? Actually, I'm going to increase. This is P, and the tip, let's say tip displacement will be U. In structural mechanics, we very frequently draw the displacement and load curve. Okay? So I'm going to increase P, and then we can find the displacement and plot. So, for example, something like that. So, at initial time, there is no force is applied. So, P equals 0, and I'm going to increase the force P. Then will be increased. So, this is a loading process. So, in static analysis, what's the concept of static analysis? Static analysis means we are increasing the load very, very slowly. Okay? To avoid the dynamic effect. If we increase the load very quickly, structure due to the inertia, the loading rate is very important. If loading rate is big, it means there is some acceleration. So due to that acceleration, inertia forces happen and structure will vibrate. So to avoid that kind of dynamic behavior, we increase the load very slowly, step by step, right? In static. Then the dynamic effect can be ignored. So now we are thinking about that kind of static procedure. So we are increasing the load very slowly, and then this is a loading process. Then we can plot some point on this load displacement curve, right? So in experiment, actually, something like that. And then we will unload, decrease the load very slowly. Then we can also get the unloading curve. This is loading curve. This is unloading. If loading and unloading curve is different, okay, that's the general case, right? this process is not reversible. If the loading curve and unloading curve is the same, this process is reversible. So elasticity means loading and unloading path is the same. So elasticity means loading path is the same to the unloading path. Okay? It doesn't matter the curve is a linear or so. For example, so this is loading path, and unloading path is this. That it's elasticity, right? Okay, that's not a plasticity or inelasticity. Okay, if path is the shape of path is not important. Okay. If loading path and unloading path is the same, it means elasticity. Now let me think about the energy. And work. What's the energy? Energy. Okay. Every day we are engineer. We are saying energy is important. We need to save energy. So every day we are saying about energy, right? But what's the energy? John, what's the energy?
Apply the force, and then the material is moving or deformation.
I mean the general meaning of energy. You are wanted to talking about elastic energy, right? Huh? So we have electric energy, heat energy, right? Chemical energy, right? So many types of different type of energy, and energy is how can I say energy? So energy is something. Energy is something that can be converted to work. Energy. Okay. Is what can be converted to do work, right? So energy can give us some work, right? Let's say a thing that can be converted to the work. So heat can make a work. Okay, electricity can make a work. What? Okay, right? Then what's the work? You definition of work. Huh? What's the work? Force multiplied by distance, right? So here we have some mass here. I like to put some force F, and if this mass move the distance in the force direction, and this distance is u, okay, the work will be a F u, right? This is your work. You already know this concept, right? No or not, you know? This is a simple concept. Maybe you learn about this in high school, right? So let's consider now that spring system. So I like to increase here, let's say time here P. I like to increase the force, something like that, step by step. Then I like to, we can plot force displacement curve P. Okay, what going to be an energy? Huh? So, for example, for this small displacement increment delta u, small work will be calculated by here the force F, P and delta U. So this bar, area of this bar will give us that small incremental work. And total work, how can I calculate total work? We need to do integration, right? P delta U from 0 to some U star, let's say this is a U star, some value U, and du. So energy, if we don't need to have du here. Then that equation gives us area of this, right? Area of this will be a work here. Area of that will be a work. When the load displacement curve PU can be represented by just a straight line, okay? right? And loading path and unloading path is the same. We are saying what? Linear elasticity, right? Linear elasticity. So linear and the meaning of the terms linear and elasticity are different, right? Linear means the straight shape of the load displaced, this straight line, and elasticity means loading path and unloading path, right? So in this case, the relation between P and K. Let's give you some K is a constant. So K will be a slope of this. Then let's put this into that equation, then work. For this case, will 0 U star, okay, Ku du will be 1 over 2 Ku square, right? Maybe we need to have a here, star here. So this work, okay, is done by externally applied load P, right? And if we unload, get rid of that P, this spring go to the initial position by what? By what? So spring is stretched, and I get rid of the force, then string going to back to the initial position. To make the spring tip go to the initial position, there should be something, right? Some driving force. How? Where that comes from? Okay? That's the energy stored in the spring. That's the, okay? So once we apply the load and the spring is stretched, externally applied force P make a work, external work, W, and amount of that work is this. And during this process, that spring store some energy. We are saying potential energy or elastic energy inside of a spring. It stores some energy inside. Energy should be conserved, right? So externally applied work should be stored somewhere. That somewhere is a spring, right? So spring store externally, so work, externally applied work is converted to the energy and stored in the spring. Understand? And that amount of the work is the same to the spring, the elastic energy stored in spring. So this amount of energy will be stored. And that stored energy will make a reversible process, right? So, for example, so let me give you an example of irreversible process. Here I have some mass here, I put this mass onto this ground, and I'm gonna push this mass. Okay, there some displacement happen, but it never go back to the initial position. Even I give some external force and external work, right? Where that external work go? Clearly, this is not a reversible process. So, no energy is stored in this book, in this mass, or in this surface, right? Where is it? Where is that work? But that work should be converted to what? To heat, because of friction. Okay, friction produce some heat and disappear to this air, right? This is irreversible process. But once we have a spring, we can make a reversible process. So in irreversible process, the externally applied work become heat or converted to other type of energy. Okay, so now you understand some concept of energy and work in structural mechanics and solid mechanics. So in this spring example, I considered displacement and force, right? But exactly same thing happen for stress and strain. You can consider force, the stress as a force, strain as a displacement. In very small the level of a material point. So in material point level, force become stress, okay, and strain become displacement. So you can think like this. So here we have a spring, and we can apply the stress, and the displacement is strain. And let's say this spring have a length 1. Let's say this is an externally applied stress. Because strain comes from displacement, stress comes from the force, right? So we can make this kind of model. Then we can also plot strain stress curve. And if we increase the stress, also strain increase, there are going to be some curve. And this area is we are saying free energy. And that small incremental energy is a D and D free energy. This is a free energy. So same meaning. In material level, so that incremental in the free energy will be a stress D strain. This will be a D strain. And here stress. Right? So free energy store in free energy store. Or you can think this is just a strain energy. You can think this is a strain energy. So in mechanics, in general, strain energy and more elastic energy or potential energy are all the same thing. Okay? So and here sigma D will be a incremental external work. So work, externally applied work, will be stored in the body or spring here as a free energy. So if we look at this equation, we can simply find stress can be calculated from that energy. So right? If you divide both sides by D strain, we can have this equation. Here, usually free energy should be a function of strain. And if the elastic, let's consider linear elastic case. Linear elastic case. Stress and strain relation is a linear, like this. And energy stored will be a one over two, and let's say the slope of this is a 1 over E, and strain square, right? This is the area of this triangle, right? So we are saying this is a elastic modulus. Stress can be calculated from the free energy. Okay, let's put this result into here. Then E. We can calculate the relation between stress and strain from the energy stored in the spring, right? And here the modulus E can be calculated by one more. If we take the derivative about strain, then we can have this, right? This means this can be a twice square if you take the derivative about strain twice on free energy, we can calculate the slope of this curve, right? We can calculate that material constant. So from this process, anyway, we found the relation between stress and strain in that simple one-dimensional case here. And we are saying this is a material law. Or constitutification. Right? Okay? So, okay.